Hello, can everyone hear me? I'm not sure if my mic is working. Okay, thank you. So for the tutorial today, we will just talk about Bayes formula and independent events. Bayes formula is actually just derived from conditional probability that we discussed on Monday, so it's really nothing new. If we recall the conditional probability formula, we know that probability of A given B is equal to probability of the intersection between two sets divided by probability of B. And similarly, we can have probability of B given A is probability of the intersection divided by probability of A. From the second formula, if we cross multiply, we will have probability of the intersection is equal to probability of A times probability of B given A. And we can substitute that into the numerator here. We can rewrite probability of A given B. Instead of writing probability of the intersection, I can just use the whole expression here. And this one is called Bayes formula. You can choose to memorize it, or you can choose to understand how it works. It's really up to you. But I recommend the second one, because if you think about it in the end, because you will not be given any formula sheet for this course, it will be a lot of formula for you to memorize. So I would just suggest you to understand this kind of derivation is pretty simple. Next one, we talk about independent events. We say that event A and event B are independent if you know some information about A does not tell you any information about B. This concept is often being mistaken with mutually exclusive, but they are not the same concept. They are very different. For example, the event that you passed TUT0107 and the event that your friend passed, let's say Math 102, they're independent event, because if you know information about whether you pass 107 or not, it does not increase or decrease the chance that your friend can pass Math 102 or not. However, if you have the event like today is raining and today is not raining, then they are not independent events. They are mutually exclusive events. If I call A is the event that today is raining, and B is the event today is not raining, then we know that if A happens, then B does not happen. Which means if we know some information about A, it decreases the probability that B can happen. So information about A actually tell you some information about B. Therefore, they are not independent. However, they are mutually exclusive, because if A happens, then B cannot happen. And if B happens, then A cannot happen. Does this part make sense? You will see some tests to test for independence between two events. Is that probability of the intersection is equal to the product of each probability. So if the probability satisfy this equation, then A and B are independent. And if A and B are independent, it has to satisfy this equation as well. If somehow you have that probability of the intersection is not equal to probability of A times probability of B, then you know for sure that A, B are not independent. You can also see another notation like if A and B are independent, then probability of A given B is equal to probability of A given B complement equal to probability of A. You can for sure prove this, but you can also understand intuitively because our definition is that A and B are independent if information about A does not reveal any information about B. So here what it's saying is that given that B happened, which means that given that we know some information about B, then the chance that A happened is the same as when we know some information about B prime. And it is the same when we don't know anything about B. Probability of A is just probability that A occurs in general when we don't know anything about B at all. So whether we know B happens or not, it does not affect the chance that A happen. That's what this expression means. And you have to remember that if A and B are independent, then they are not mutually exclusive. And if they are mutually exclusive, then they are not independent. However, you cannot say that not independent means mutually exclusive. This implication is wrong. And you can also not say not mutually exclusive implies independent. This is also wrong. You can only say the first one and the second one. If you learned about logic, they are actually the contrapositive of each other. So logically, they are equivalent. Any question about this concept? Make sure that you distinguish very clear between independent and mutually exclusive. It is tested all the time. If there is no question, I will let you work on question 1. If there is anything confusing, you can put in the chat for me. Okay, so for this question, we know that the insurance classifies a customer into two categories, and 65% are good customer. So the chance that someone being a good customer is 0.65, which means the chance that they are a bad customer is 0.35. I just take 1 minus 0.65. And then given that the customer is a good customer, the probability that they make a claim in a particular month is 2%, which means the probability that they did not make a claim is 0.98. For a bad customer, the probability that they make a claim per month is 0.07. So the probability that they did not make a claim is 0.93. When you draw the tree diagram, you can exclude these two branches because we do not touch it in this question. However, like if you just want to draw a full tree diagram, you can for sure just draw all of it out, because it's always safe to check that at each branch, your probability add up to 1. Because if it does not add up to 1, you just construct a wrong tree diagram, then you will get wrong answer as well. The question is asking for probability that the last claim is made by a good customer, which means we know that the customer made a claim. And we're interested in the chance that the customer is a good customer. So we want to calculate probability of G condition on C. Using conditional probability formula, I can have probability of the intersection divided by probability of C. And here you can have it using base formula is probability that the customer made a claim, given that they are a good customer, multiply with the chance they are a good customer, divided by probability of C. Probability of C is just probability of making a claim and being a good customer, and make a claim and be a bad customer. Because the insurance company classifies its customer into two categories, so there is no other categories that they can belong to. The numerator, probability that the customer make a claim given they are a good customer, is this number, 0.02. Probability that someone is a good customer is 0.65. In order to calculate these two expressions, you can use the same idea. If we look at the tree diagram, probability that C intersects G is this path. So you just take two numbers multiplied together. And C intersect B is this path here. You just need to take two numbers and multiply together. And after you plug in the calculator, the final answer will be what you are expecting. Any question about this one? You will see that most of the question today about Bayes' formula is basically just conditional probability that we learned before. If there's no question, I will let you work on this one. So my tree diagram, the first column, it represents for what is the color of the ball that I pick from box 1 and put in box 2. And this column represents for the color of the ball that I picked from box 2. So I first pick a ball from box 1. Initially, I have 4 red and 6 black. Then the chance that I got a black one, let's see. Yep, I see a student answer. It looks correct. So 6/10 for black one. Because you have 6 black balls originally, and you have 10 balls in total. You have 4 red, so probability of picking a red ball would be 4/10. Now I will need to figure out the probability for each branch here. So B2 would be 7/11 and R2 is 5/11. Let's see. So if I pick a black ball from box 1 and put in box 2, now box 2 will have 4 black. Then like the students say, we have 11 balls in total. Out of that, 7 is red. So 7/11 for red and 4/11 for black. How about this one here? What would be the probability if we use exact same idea? Yep, look right to me. If the first ball you got is red and then you put in the box 2, now box 2 will have red ball, 8 red balls. So in total, you have 11 balls. Out of that, 8 is red. So 8/11 for red and 3/11 for black. So this complete our tree diagram. We are interested in probability that the ball we selected from B1 and placed into B2 was red, given that we got a red ball from B2. So I want to find probability that I pick a red ball from box 1, given that I got a red ball from box 2. So this is just probability of the intersection divided by probability that you pick a red ball from box 2. And you can see R1 intersect R2 is this path. So you just need to multiply 2 numbers together. And probability of red 2, we will look for whatever outcome that have red 2. We have 2 outcomes. So we will add them together. The first outcome is in this path. We multiply them. And then the second path is this one here. We also multiply them. And if you put in the calculator, you will get a final answer. Any question about this one? If no, I will let you work on question 3. Is it the probability that she guessed a question wrong? Guess a question correctly squared. Why is that? I haven't calculated myself. So here we know that she knows the answer to a question is 80%. So probability that she know the answer is 80%, and which mean probability that she doesn't know the answer is 20%. Given that she know the answer, she will answer it correctly. Then probability that she answer it correctly, given that she know the answer, is 1. And probability that she answer it wrong, given that she know the answer, is 0. Similarly, for the second question, so if she doesn't know the answer, then she have to guess randomly. Each question have 3 possible answers. So the chance that she got the answer correctly, if she doesn't know the answer, is 1/3. And probability that she got it wrong is 2/3. Do we also do K and K prime for the second question? Doesn't this assume that either she know both answer or doesn't know either? Yes, we do assume that. Just for the sake of simplicity, I think this should be worded like better, but this is the intended answer that they want. What if she knows one but doesn't know the other? Yes, that's possible as well. But I think they can word it like better for the intended answer that they want. Let's assume that is like this here, either that she know both or she doesn't know both. I know sometimes statistics question, if you think about it, what can happen in real life, it actually give you many possibilities. I'll fill in the same answer here too. If you see this question in the test and you feel like maybe the way you're thinking is a bit more complicated, you can always ask the professor or the TA to clarify the question. So here, I want to calculate the probability that she guessed both of the answers, given that she answered them correctly. And I just use probability that we have the intersection divided by the probability that she got both of the question correctly. The intersection between guessing and getting 2 correct answer is this path here. So I take 20%, multiply with 1/3 and 1/3. And probability that she guessed both of the answer correctly is in 2 paths, this path and this path. So there's no possibility that she knows one but not the other. Realistically, yes. But for this intended answer, no. I can also upload another solution later about how to solve the problem if we don't have this assumption. Does that make sense? Yeah, I can definitely post it later. Is there any other question about this one? If no, I will let you work on question 4. Okay, so here we know that the population that suffer from A only is 20%. So I put 20% to this part because it is A only. And then suffer from B only is 12%. So I put it in here, which is B only. And suffering from both is 4%. So I put it in the middle like this. And the question is, are the occurrence of two diseases independent? What do you think? If you just look at these number, do you think they are independent? We can do this using algebra, right? Yes, you can. What you can test is check whether probability of A intersects with B is equal to probability of A times probability of B or not. You can for sure check this. If they are equal, then the chance that having two diseases is independent. But if they are not equal, then the chance that you having two diseases is not independent. So the students say that they got probability of A times probability of B is 0.0384. And the intersection is 0.04. Hopefully that the number is right because I didn't calculate. But another way you can look at this is that we discussed about if A and B are independent, then probability of getting A given that getting B is the same as probability of getting A given that you do not get B, right? And according to the Venn diagram, if B, like if the patient got disease B, then the chance that they got disease A is 4% over 16%. And the probability that they got A given that they did not get B, I think this is more complicated number than I thought. 20% divided by 1 minus 16%. But then eventually you will see that those two numbers are not equal as well. So A and B are not independent. You can use either two ways. How do you get PA times PB? So here, probability of A is the whole circle, right? You just take probability of A without B plus probability of A with B. And then you would have probability of A. Yep. And they ask if the probability increase or decrease if you know that he or she also suffer from B. So without any information about B, then probability that she got disease A is 24%. And then given that the person got disease B, then the chance that they got disease A is 4 divided by 16. Hopefully that I calculated correctly. This is 1 over 4. And I think is larger than 24%, right? Which means that knowing that the person got disease B, it increased the chance that they got disease A. Any question about this one? Let me know if anything is unclear. Otherwise, it's the end of our tutorial and good luck with your quiz.